it's traditional to talk about the uncountability of the real numbers. So Cantor's big result was that the set of all real numbers is an uncountable set. So maybe if we're going to talk about countable sets, then I would suggest that we talk about Hilbert's Hotel, which really makes that idea perfectly clear.
Yeah, let's talk about the Hilbert's Hotel.
Hilbert's Hotel is a hotel with infinitely many rooms. Each room is a full floor suite. So there's floor 0. I always start with 0 because for me, the natural numbers start with 0, although that's maybe a point of contention for some mathematicians. The other mathematicians are wrong.
Like I mentioned to you, I'm a programmer, so starting at 0 is a wonderful place to start.
Exactly. So there's floor 0, floor 1, floor 2, or room 0, 1, 2, 3, and so on, just like the natural numbers. So Hilbert's Hotel has a room for every natural number. And it's completely full. There's a person occupying room n for every n. But meanwhile, a new guest comes up to the desk and wants a room. Can I have a room, please? And the manager says, hang on a second, just give me a moment. And you see, when the other guests had checked in, they had to sign an agreement with the hotel that maybe there would be some changing of the rooms, during the stay. And so the manager sent a message up to all the current occupants and told every person, hey, can you move up one room, please? So the person in room 5 would move to room 6, and the person in room 6 would move to room 7, and so on. And everyone moved at the same time. And of course, we never want to be placing two different guests in the same room, and we want everyone to have their own private room. But when you move everyone up one room, then the bottom room, room 0, becomes available, of course. And so he can put the new guest in that room. So even when you have infinitely many things, then the new guest can be accommodated. And that's a way of showing how the particular infinity of the occupants of Hilbert's Hotel, it violates Euclid's principle. I mean, it exactly illustrates this idea because adding one more element to a set didn't make it larger because we can still have a one-to-one correspondence between the total new guests and the old guests by the room number, right?
So to just say one more time, the hotel is full.
The hotel is full.
And then you could still squeeze in one more. And that breaks the traditional notion of mathematics and breaks people's brains about when they try to think about infinity, I suppose. This is a property of infinity.
It's a property of infinity that sometimes when you add an element to a set, it doesn't get larger. That's what this example shows. But one can go on with Hilbert's Hotel, for example. Maybe the next day, 20 people show up all at once. We can easily do the same trick again, just move everybody up 20 rooms. And then we would have 20 empty rooms at the bottom, and those new 20 guests could go in. But on the following weekend, a giant bus pulled up, Hilbert's bus. And Hilbert's bus has, of course, infinitely many seats. There's seat 0, seat 1, seat 2, seat 3, and so on. And so one wants to, all the people on the bus want to check into the hotel, but the hotel is completely full. And so what is the manager going to do? And when I talk about Hilbert's Hotel, when I teach Hilbert's Hotel in class, I always demand that the students provide, the explanation of how to do it. Mm-hmm. So maybe I'll ask you, can you tell me, what is your idea about how to fit them all in the hotel, everyone on the bus and also the current occupants?
You separate the hotel into even and odd rooms, and you squeeze in the new Hilbert bus people into the odd rooms, and the previous occupants go into the even rooms.
That's exactly right. So, that's a very easy way to do it. If you just tell all the current guests to double their room number, so in room n, you move to room 2 times n. So they're all going to get their own private room, the new room, and it will always be an even number because 2 times n is always an even number. And so all the odd rooms become empty that way, and now we can put the bus occupants into the odd-numbered rooms.
And by doing so, you have now shoved in an infinity into another infinity.
That's right. So what it really shows, another way of thinking about it is that, we can define that a set is countable if it is equinumerous with a set of natural numbers. And a kind of easy way to understand what that's saying in terms of Hilbert's Hotel is that a set is countable if it fits into Hilbert's Hotel, because Hilbert's Hotel basically is the set of natural numbers in terms of the room numbers. So to be equinumerous with a set of natural numbers is just the same thing as to fit into Hilbert's Hotel. And so what we've shown is that if you have two countably infinite sets, then their union is also countably infinite. If you put them together and form a new set with all of the elements of either of them, then that union set is still only countably infinite. It didn't get bigger. And that's a remarkable property for a notion of infinity to have, I suppose. But if you thought that there was only one kind of infinity, then it wouldn't be surprising at all, because if you take two infinite sets and put them together, then it's still infinite. And so if there were only one kind of infinity, then it shouldn't be surprising that the union of two countable sets is countable. So there's another way to push this a bit harder, and that is when Hilbert's train arrives. And Hilbert's train has infinitely many train cars, and each train car has infinitely many seats. And so we have an infinity of infinities of the train passengers together with the current occupants of the hotel. And everybody on the train wants to check in to Hilbert's hotel. So the manager can again, of course, send a message up to all the rooms telling every person to double their room number again. And so that will occupy all the even-numbered rooms again, but free up again the odd-numbered rooms. So somehow we want to put the train passengers into the odd-numbered rooms. And so, well, every train passenger is on some car, let's say car C and seat S. So somehow we have to take these two coordinates, C, S, the car number and the seat number, and produce from it an odd number in a one-to-one way. And that's actually not very difficult. In fact, one can just use, say, an easy way to do it is to just use the number 3 to the C times 5 to the S. 3 to the C, 3 to the car number. So 3 times 3 times 3, the number of the car. You multiply 3 by itself, the number of the train car, and then you multiply 5 by itself, the seat number times, and then you multiply those two numbers together. So 3 to the C times 5 to the S. That's always an odd number because the prime factorization has only 3s and 5s in it. There's no 2 there. So therefore, it's definitely an odd number. And it's always different because of the uniqueness of prime factorization. So every number can be factored uniquely into prime. So if you have a number of that form, then you can just factor it, and that tells you the exponent on 3 and the exponent on 5. And so you know exactly which person it was, which car they came from, and which seat they came from.
And prime factorization is every single number can be decomposed into the atoms of mathematics, which is the prime numbers. You can multiply them together to achieve that number. That's prime factorization. You're showing 3 and 5 are both prime numbers, odd. So through this magical formula, you can deal with this train infinite number of cars with each car having infinite number of seats.
Exactly right. We've proved that if you have countably many countable sets, then the union of those sets, putting all those sets together into one giant set, is still countable. Because the train cars are each countable, plus the current hotel, it's sort of like another train car if you want to think about it that way. The current occupants of the hotel could, have the same number as any of the train cars. So putting countably many countable sets together to make one big union set is still countable. It's quite remarkable, I think. When I first learned this many, many years ago, I was completely shocked by it and transfixed by it. It was quite amazing to me that this notion of countable infinity could be closed under this process of infinitely many infinities adding up still to the very same infinity, which is a strong instance, a strong violation of Euclid's principle once again, right? So the new set that we built has many more elements than the old set in the sense that there's additional elements, but it doesn't have many more elements in terms of its size because it's still just a countable infinity and it fits into Hilbert's hotel.